A pulse which is 500 picoseconds wide is much, much less than the orbital period. Now, as you probably know, there's a whole other area of AMO physics which is evolving, which is the ultra-fast, ultra-intense. It's nowadays possible to produce really, really intense attosecond pulses in the vacuum UV. So people today have gotten very interested in, if I take one of these super high power short pulse lasers and I convert it into a train of attosecond pulses, for example, now how does a ground state atom respond to this? Because the electric field is very much greater for a ground state atom than what's holding the electron into the nucleus. So this is, we at Rice don't do this, but that is another very exciting area of AMO physics, is life in the ultra-fast, ultra-intense regime. We get to it by cheating. We go to an atom which is physically large, so its ultra-fast, ultra-intense regime is volts per centimeter and sub-nanosecond pulses. But these guys are talking about attosecond pulses with electric fields of 10 to the 8, 10 to the 9 volts per centimeter, effectively in the oscillating field. And that's a very hot area too. Lots of really exciting developments are coming out of that.
Yes?
Can you predict any future research direction or practical application using photon beads?
Using what?
Photon beads.
Photon BEC? Well, photon BEC is a laser.
The photon, it realized last year in Europe.
Yeah, this was in a cat.
Yeah, it
Photon
was
captive,
interesting.
yeah. BEC and photons.
Yeah.
In a cavity?
Yeah, it's different from
Cavity
a-
experiment?
Yeah. They could actually get photons.
Yeah.
to-
Cold.
to go cold into a single
Thermal equilibrium. The short answer is, can I think of an application? I can't.
Can you explain what that is for those that...
Yeah, I am not so familiar with that experiment, but I guess it's some kind of a cavity that's in the thermal equilibrium with a black body somehow. I'm not.
Yeah, I have to get the.
I don't remember how
I
it's done.
saw an article about it, but they didn't internalize it.
Sorry.
Huh? Theorists always
I'm surely read the paper.
Well, maybe you can cut up. Asking the question.
Yeah, tell us how the experiment works.
It's basically a cavity, two mirror on the cavity. Inside is a dye molecule, and they use the lens is on the scale of micrometer, and they form basically the transverse mode is very broad, and the BC they form is basically the 0-0 mode instead of the very broad mode. And they observe a very, very tiny spot coming out of the cavity, and that's what they call photon condensate.
So they observe light coming out of the cavity as coherent emission.
And, basically single mode, narrow distributed.
Yeah. So I mean, it's very similar to a laser. So I mean,
How is it different?
I think it basically is. I think the difference is not huge. It was more of a, I'm remembering it very vaguely. I think it was more of just a little bit different interactions between the. I'd be overstepping what I'd say. I think it's just slightly different cavity configurations and gain media, so you get little different selection processes that create the quantities of the photon field compared to the standard laser, where it's basically just you have lots of different modes of the cavity, and the one with the highest gain is the one that's populated, and that's in the laser. It's hard to imagine exactly what could be very different from that to get this other experiment to work, because Chang just described as laser.
So speaking of lasers, what kind of lasers do you use in that?
We use a combination of lasers. For doing the excitation of the atom, we use either diode lasers, external cavity diode lasers, or dye lasers, which we need a lot of power, although we're in the process of phasing those out. And then we use, for trapping, we use infrared lasers, which are typically fiber lasers. And for optical lattices, they're also infrared, about one micron. And there you can use a seeded fiber laser. So you use an external cavity that seeds a fiber laser, single frequency. And that's used to produce standing waves that give you an optical lattice. They get very used, mainly dye lasers.
Dye lasers, dye sapphire lasers are the ones that we principally use. We use some stabilized helium neon lasers as a frequency reference. And then we have a slightly different, Randy requires lasers that are very stable one relative to the other. We require ones, since Rydberg levels are very closely spaced, the laser has to stay fixed to megahertz per day. And if we do a rastering scan, it's going to be good to a megahertz anywhere in that scan. And that's actually still a challenge. You can't commercially buy something that does that. So we use helium neon lasers as a frequency standard to the transition in neon. And then we reference to that. So our hard job is actually stabilizing the lasers rather than they're commercial lasers, but it's locking them to.
How do you reference it to the heating?
With a scanning fiber power with two beams going through. And if you make certain assumptions, you can do it very easily.
How do you do it?
Well, if you take a scanning fiber repair, right, as you vary the separation, you'll get transmission peaks. They'll be for the different wavelengths. And then what you can do is you can pick out a transmission peak, say in the visible that we're using, say in the yellow, and then one in the red. And if their relative position changes, it means their relative wavelengths are changing. But the helium neon laser is stabilized. It's good to better than a megahertz a day. So you adjust the visible one so it always stays at exactly the same step. And you say, well, doesn't the whole cavity drift? The answer is yes, it does. But provided that you've got a linear space, a linear drive, and you're spacing it, then both peaks move.
But you don't get a megahertz, right? So how do you deal with that? I mean, so if they're moving,
the separation, if you've got a linear ramp and it stays linear,
yeah,
the separation remains the same.
You have to stabilize the Febvre-Barreau cavities.
It's pretty well stabilized. I mean, as we all do. I mean, people that work in AMO physics, often one of their tasks is make a new laser that will do particular things that we want. So, you know, my students, I've often had a student who was called the laser jock, because he was developing the next generation of lasers to do a particular experiment, because he couldn't go out and commercially buy what we needed. And I think that's still largely true, that if you looked at the lasers in many of the systems in our labs, they're not commercial. They're based on commercial systems, but they go beyond what you can do commercially.
So a question for, I guess, the cold atom guys. So as we push towards lower and lower temperatures, say with your, say with fermions, as you get to lower values of T over TF, right? Eventually you start running into the problem that if your momentum distribution becomes very close to that zero temperature distribution. So can you comment a bit about some of the new ideas in terms of how to actually measure temperature when we are, say, 5% of the Fermi temperature or even lower? How can I tell the difference between 5% and 6%?
So that's a real problem in the field, to be able to distinguish. So the problem is in a Fermi gas, even as you go to T equals 0, there's still finite energy remaining in the atoms. So this is the famous Fermi pressure. So it's like in a white dwarf star. Even though it's very, very cold, if at T goes to 0, much less than TF, the remaining energy is all the Fermi energy. And so that can be a lot. And so if you have a thermal energy, which is a few percent of that Fermi energy, it's going to be very, very difficult to see those effects. And so one of the nice things that has happened just very recently is that a group in France has realized that or experimentally realized, actually this is where theory came first, this is the idea of Jason Ho, that you can relate the internal pressure to a density in a trap. So if you relate turned out the axial density, which is like the linear density in a confining potential, is related directly to the pressure internal pressure of the gas, which is in turn related to the temperature. And so that's been a way of calibrating temperature at very low temperatures. For the particular case that you're at, what's so-called unitarity limit, this is where the interaction scattering length goes to infinity. And at that point only, this works pretty well.
And the challenges are actually not, different regimes, different examples, but not so different than same kind of challenges that people ran into in condensed matter physics, measuring low temperatures. Eventually it gets hard to do it, and you have to be creative and find other things. So maybe you can't measure the temperature of your sample, but you stick something onto your sample that comes into thermal equilibrium, and you can measure the temperature of that, and then your problem's done. So you can, there's still a lot of potential to put another gas in there that can probe the temperature and be as a proxy. You worry about it being in thermal equilibrium, but that's a powerful technique as well.
So I guess we're getting close towards the end of time. Do you guys have, say, any advice for people just starting out in the field here, being grad students as we are?
Starting out in AMO physics?
Yeah.
Or starting out just in physics?
Well, I'd like to hear about AMO, but I'm not sure how this
It probably translates pretty well, but my best advice is that if you're just starting out in physics, don't worry about what area you're going into so much that you feel like you need to be in something which is very applied in order to get a job or something like that. Because there's a lot of, especially in AMO physics, there's a lot of good training that you get in the laboratory, which is very applicable to many, many different areas of endeavors, many different areas of physics. So the experimental techniques are, very general and so on, and get to be able to, you do a little bit of theory, which helps, a little bit of numerical work. So my best advice is don't try to predict what's going to be hot in 7 years from now, but just do what interests you. Do what's exciting. You came to graduate school presumably because you like physics and you want to do physics and you want to do something which is fun. You want to do something which is exciting. You want to do something which is new that people hadn't done before. Do that, and don't do something that is boring or is hopefully land you the right job. Don't do that, because if you're doing something boring you're not excited about, you're not likely to get that job. You're going to do your best work if you're really excited and jazzed and turned on. So do something, pick projects in areas that are fun and exciting.
But the wonderful thing is that atomic physics is fun and exciting, and it's the perfect choice.
The skill set you get is amazing. I mean, people who come in my lab have gone off and work in 3-5 semiconductors, in optics, and optical communications. They've gone and worked in oil companies and geophysics because of their modeling skills.
And in academia.
But just go into a field where you're going to come out with a wide array of skills and enjoy what you do, and you'll find it. You'll find a job. I have all graduate students driving a cab. Okay, and they've all got positions, and they've all been multiply recruited, and people have been coming back for more. So AMO physics is a very good training.
It's got that graduate student who is a general.
Well, yes. Well, he's the Secretary of the Army. Actually.
Yeah, Secretary of the Army.
But he was the youngest general ever, head of CEO of
the black sheep of his family.
But apart from the choices, whatever field you are, make sure you don't get. You have to burrow down deep into your PhD thesis and your project, but make sure you pay attention to what's going on in the field, at conferences, and keeping up with the literature to make sure you have a broad knowledge of what's going on, because different areas in the field don't stay forever. They come and they go, and you have to be ready to pick up the next one. You want to be aware of what's going on. So it's important to really keep your eyes open, not just thinking about my project. I would say to new students, that's a very important thing. When you go to conferences, don't just go to the sessions where you know everybody and everything going on, but try to get a good overview of things as well.
Would that also apply to theory too?
Yeah, I think that's pretty much it in terms of time. So I'd like to say thanks to all of our